Hey, this is Brock Lemires, and in this video, I'm going to talk about sources of electric energy and specifically the battery. So when you think about electrical engineering, one of the things that I always think about is, well, where does all this electricity come from? And it turns out that there are three primary sources that we use for electric energy in society. And those are the battery, electric generators, and solar cells. And these make up the vast majority of the sources of electric energy that is in use today. So in this video, I'm going to talk about specifically the battery. Okay, so recall when we looked at the periodic table that there were groups of different atoms that behave differently. And one of the largest groups was the metals. And a metal was something that could allow its electrons to flow out or flow in very easily. And we define this thing called an ion, which is where under a neutral condition, there's an equal number of protons and neutrons in an atom. And so there's no net charge. But if a metal gives away some electrons, then all of a sudden it has a positive charge because it has more protons than electrons. And so that becomes a positively charged atom. And similarly, some metals can take on additional electrons. And so if you take on additional electrons, that's more negative charge. And now you have more negative charge than the positive charge given by the protons. And so you have a negative charge. And so remember the name we give to an atom that is charged is called an ion. And it's nothing special. It's just an extra few electrons or a few less electrons than its neutral state. And then we define these terms called a cation, which is the positive charge. So that's when you have fewer electrons and protons where it gives away its electrons. And then we have an anion. And the anion is a negative charge where you have a material that has more electrons than protons. And these are all just metals. Okay, so let's look at the basics of a battery. Okay, so we're going to have, if we have materials that can have, that we can either put them into a particular state where they have fewer electrons and protons or more electrons and protons, we can create a situation where we have the building blocks of a battery. And so let's take a look at this. So let's just say that we have a material that has fewer electrons, and that's going to be our cation, and that will be the positive charge. And then let's say that we have another material, which is going to be the anion, and that's the negative charge. So you can see right away, it's like, well, look at this. This one wants, this has more electrons than its neutral state, so it kind of wants to give away electrons. And this one has fewer electrons in its neutral state, so it kind of wants electrons to flow in here. So if we drew like the flow of electrons, just by looking at just the charge on these things, you would think that electrons would potentially want to cruise over, and do this sort of thing. Okay, and it turns out that that is then the first part of a battery. It's coming up with materials that act like an anion or act like a cation, and these are always metals. Okay, and so when we think about a battery, we're going to give some names to kind of the connections here. So number one, let's define a few terms. A cell is one of these cation / anion, we'll just call it objects. Okay, and a cell represents, you can basically think about it where you're going to create a voltage and you're going to allow electrons to flow, and you can kind of tell that depending on like the size of the materials that are used here for the cation and the anion, or just how many electrons they can give or take, you can kind of see that they're going to be stronger or weaker. But what happens with cells is that they typically put out a fixed voltage, okay? And these voltages are not as high as you might think. It's not like they're 12 volts. These things can range from, 0.7 volts, 0.75, 1.5, 2 volts. And then what you do is you can build a higher voltage by stacking multiple cells on top of each other. And that's how you get to like a 9 volt or a 12 volt battery. But what we're always talking about when we look at the kind of the chemistry and the physics behind what's happening in the battery, we're just looking at the cell itself, which is a cation and an anion. Okay, another term that we want to define is what we call an electrode. Okay, so the definition of electrode is where current enters or exits a device. Okay, so this is where current enters or exits. Okay, and so even though we're just drawing one cell, this could potentially be a lot of different cells. So it could be like cation, anion, cation, anion, cation, anion. But for us, we just want to look at like what are the terminals? How do we get in and out of this thing? And so we define those as the electrodes. And so we'll always draw them in our little cartoon version of the battery. It's kind of the outermost ion and the outermost cation. Okay, and we also want to start labeling like them something descriptive, like positive or negative. So what we're going to do is we're going to name the electrode on the cation. We'll call this the positive electrode. And then what we'll do is we'll call this the negative electrode. Okay. All right. And so then that defines kind of, is starting to look more like a circuit. One of the things that is a little bit confusing with batteries, and I just recommend not even worry about it, is sometimes you'll hear people talk about the cathode and the anode, and that's like a way to say electrode, but also kind of indicate whether it's receiving current or giving current. And so with the battery, it's kind of interesting because it can be very confusing when you think about cathodes, because a cathode, the definition of it is it's the terminal where current leaves leaves the device. And so if you think about this, current is kind of like flowing this way, right? So it's actually flowing this way. So in this situation, it would be the cathode would be over here. But what happens is that it switches when you have a negative device or a passive device. So this is an active device, so this sources current. But if you have like a passive device, which we'll see later, then the cathode will flip over to the other side. So don't even worry about cathode right now. This is just introduction to batteries. We will always call it positive electrode and negative electrode. So that's where we're at, and we have those little terminals. And let me update my drawing there. Okay, so we got it. All right, life is good. Now, here is the interesting part about this. We don't want to put these things together, right? So you're building a battery, you would never come along or you wouldn't want to do something where you take your cation, you take your anion, and you physically touch them together. The reason is that it would cause a reaction because there is a pull between these things. So you have a positive and a negative charge. They want to react with each other, or at least pull the charge toward this junction. And so you'd have some stuff that would happen right here. We don't want that reaction to happen. What we want to do is we want to force all the electrons to go this way. Okay, so we have to insert something here that is going to, number one, first and foremost, keep electrons going one way. Okay, so we got to have the electrons only going one way in order for the battery to work. And this material that sits within here is called the electrolyte. Okay, so we're going to draw this right here. And so this is called the electrolyte. All right, and its first job is to prevent electrons from flowing backwards. Okay, so we don't want our electrons flowing to the cation when it sits here. And the electrolyte is also it also has a couple other things that are really amazing things. You got to hand it to the chemists on this whole electrolyte business, because it not only does it keep the electrons from going this way, but it also has two reactions that happen simultaneously when you connect something that allow this thing to sustain current. So let's start with this. If we then put a connection here, so if it doesn't have a connection, nothing's happening other than it's preventing electrons from flowing this way. If you connected it, okay, so let's say you connected this to, light bulb here. There's a light bulb. So that's a little light bulb, and you put a path there. Now all of a sudden electrons can flow. This electron right here will want to go over here. Because it finally sees a path, a conduction path, to get over to a positive charge. So it's like, oh, opposites attract, I'm out of here. And it's going to want to go this way, okay? But the problem is that, we think about electricity as it needs to always flow in a loop, and we need to sustain this, okay? So we don't just like take the electrons that exist in the anion and instantaneously go, and then all of a sudden it's done. So instantaneously the battery's dead. We need some way to like create more electrons, and insert them into the anion in order to sustain this. And so this then becomes a reaction when you have a circuit here that will actually produce electrons and put them into the anion so that these electrons can continue to flow. And that's the second part of the electrolyte. So what it does is it creates this a reaction right here, and it's actually called oxidation. We don't necessarily care too much about this in electrical engineering. This is just more chemistry, but it's an oxidation reaction, and that's just the term you use for any chemical reaction that loses electrons. And so basically, it reacts right here on this boundary, and these electrons they lose them into the anion, and it sustains this flow of electrons, and so it'll keep going and going and going. So it's like, okay, there's step 2 of what the electrolyte does. And then finally, step 3 is, well, here comes these electrons. Where are they going to go? If you didn't have a reaction over here to create more positive charge, what would happen is that you'd have all these positive charge, and they would be filled up with, or they'd pair up with electrons, and all of a sudden there's no net charge, and the reaction would stop. And so what you need like an opposite reaction as this little fellow that creates the electrons. You actually need another reaction right here, which creates positive charge, or what we say positive ions. They're really holes, right? And so you need like this reaction at this boundary right here, so that the electrons continue to be pulled over into here. And this reaction is actually just called it's called reduction. And so let's see, I'll write that down here just to keep it consistent. So this is called a reduction, and that just means that it is a reaction in which it absorbs electrons, okay, or it gains electrons, okay. So that's all the difference. So that we call this a reduction, a redox, okay. So the redox reaction, oxidation. Anyway, this electrolyte is like a little beautiful chemistry reaction that does 3 things in a battery, but now you actually have a battery. And look at it, when you connect the flow here, what happens is that the electrons only can flow one way, so they come over here. You have a reaction right here at this junction that produces more electrons to sustain the flow, and then you have a reaction right here that absorbs those reactions so that you continually have positive charge over here, and voila, you have a battery. And so this is pretty awesome. Okay, so now let's talk about the types of batteries that exist in our modern world. So the first class is going to be your single-use batteries. These are the non-rechargeable, so these are what you throw away. There's 2 main types, and all batteries are basically classified or characterized as what materials they use for their positive electrode, what materials they use for their negative electrode, and what material they use for their electrolyte. So the first one is zinc carbon. That's very common, and zinc carbon batteries are the cheap, short life batteries. And basically anytime you get a toy, like you buy some like toy or some sort of cheap electronics and it comes with batteries, it's always zinc carbon batteries, because they're really bad batteries, but they're super cheap. So like, for example, in a digital multimeter, this is an inexpensive multimeter that's, $10. If you pop the top off of that, you see this peak power heavy duty. If you look this up, this is a zinc carbon battery. So included with the multimeter, it's going to burn out in like probably a week. The next one is alkaline batteries. And these are your standard batteries that you buy. So this is Energizer and Duracell. And these are really good batteries. I mean, you'll notice that, these last a long time, and they're awesome. 1.5 volt is what a AAA and AA are, and C and D also. And then this is a 9 volt. This 9 volt is made, if you pop this thing open, you'd see 6 little cylinders in here that each provide 1.5 volts. And so that's how you get up to 9 volts. So they call this a 6 cell. This is just 1 cell right there. But those are your normal batteries that we think about that you throw away. The next class of batteries is rechargeables, and they call these secondary batteries. People don't use the terms primary and secondary very much anymore. This is just how they used to classify it, so it's interesting just to have it down once. But first and foremost, you got your lead acid battery. There's a lot of lead acid batteries in the world. This is what's in your cars or your boats and your motorcycles. This is what you use to start. Okay, so when you crank your car, it uses that lead acid battery to turn the starter until your combustion engine can take over. These things are huge. They are heavy. They are expensive. I mean, car batteries are $75, $100. Boat batteries, $130. And they can provide a ton of instantaneous current. Okay, they're lead acid, so a lot of these have actual, liquid in them. Okay, it's like liquid acid, but they provide a lot of juice, and they're also rechargeable. Going back to the primary, one thing I didn't mention is a lot of times you'll hear these called dry cell, and it's because the electrolyte is it's usually not a liquid. It's usually like a powder substance, so like basically just a powder that does all the things that electrolyte does, and so you'll hear them called a dry cell. Once you get down to like lead acid, there's lead acid batteries that you actually fill the electrolyte yourself as like a liquid. You pour the acid in there, and so that's why you have this distinguishment between dry cell and rechargeable. I don't know if you call these wet cells, but if you ever heard dry cell, that's just what they mean. They're basically non-rechargeable batteries that have a dry powder as the electrolyte. Okay, then you have your nickel metal hydride batteries. These are, if you've ever heard of a nickel cadmium battery, these are the ones that are rechargeable in the form factor of these things. So if you have AA batteries that are rechargeable, that you can stick them in the little charger and plug it into the wall, those are nickel metal hydride. They used to be nickel cadmium, and I tell you that because you probably heard about batteries having the memory effect. Nickel cadmium batteries were the ones that had that problem. So they were the ones that if you only burned it down to 90% and then you recharged it, it would form a memory and it would like kill the battery off. So those were the ones that it would like get used to only operating between 90% and 100%. And so those are the ones that you had to like drain all the way to nothing and then recharge up to 100%, drain to zero, recharge to 100%. So that's the memory effect of batteries, and that's where that came from, was nickel cadmium. So they replaced those with nickel metal hydride, and it doesn't have as bad a memory effect. In fact, modern batteries don't have that problem as much as they used to. It used to be a huge problem with rechargeable batteries that you always wanted to drain them to zero and then take them back up. Nowadays, people say, it's still good to do that every once in a while, but that whole issue came from these nickel cadmium batteries that are now replaced by nickel metal hydrides. Okay, and then finally the big dog, lithium ion. This is what everybody's talking about right now because this is what's used in your smartphones, in your laptops, and in electric cars. So like Teslas, they're just a giant lithium ion battery, and this is the one that has the potential to last the longest and provide a lot of current. So this is kind of like the future everybody's hoping is lithium ion. They're hoping that's going to replace lead acid, because lead is kind of toxic. But anyway, those are the main types of batteries that we have today. Another thing that is interesting about batteries is their capacity. And so it's basically like, how much current can this thing give and for how long? And so they give the ratings for batteries as amp hours. Sometimes you'll see it as milliamp hours. And what that means is they basically say, okay, if I give you an amp hour rating of 1 amp hour, that means if you pull 1 amp out of this battery, it will last 1 hour. Okay, and so then you calculate from there. So for example, let's say you had a circuit plus or minus and you put like 1.5 volt across it, and then you had something like this, and you had a resistor out here, and you pulled, let's say, 250 milliamps, and you came along and said, well, this is the rating of the battery that's giving me 1.5 volts. How do I figure out how long this circuit will last before the battery's dead? Well, you just basically take a look at the units, and the delta time is going to be the capacity divided by the current draw. Okay, and you can just kind of see the units there. So for example, if I wanted to figure out this circuit, how long could 1 amp hour battery provide 250 milliamps to here? You obviously know it's going to be 4 hours, but the way you do it is you'd say 1 amp hour, okay, divided by 250 milliamps. Okay, and so that would end up being, the amps would cancel. You'd obviously go 250 times 10 to the negative 3, and you'd be left with 4 hours. Okay, and so it could power that for 4 hours. So let's take a look at some of the ratings of like a common battery. It's a AAA battery is 1.5 volts. That's one cell, and it has a rating of 1.2 amp hours. A AA battery is 1.5 volts again, and it has a rating of 2.7 amp hours. And so you go, what is going on? They're both 1.5 volts. It's like, this one's bigger than that one. And the answer is, yeah, it is. They're both exactly one cell. It's just that there's more material in the AA. And as a result, what you get is more amp hours. So you get 2.7 amp hours on this big AA versus 1.2 amp hours on the AAA. And so it's kind of a trade-off of size, but both of them are 1.5 volts. A C battery, which is quite large, it has 8 amp hours, which is huge. D, which is the big dog, I mean, it's like huge, flashlights and radios, that's 12 amp hours. And then you go over to this guy, 9 volts. And this only has 500 milliamp hours. And so that means that only if you pulled 500 milliamps out of this thing, it would only last 1 hour. It's way less than these 1.5ers. And the reason is that you get 9 volts. So inside of here, there's 6 1.5 volt cells, little cylinders. And so you get 9 volts, but at the expense of milliamp hour. So you can just kind of trade off between these two depending on what your application is, of whether you need the higher voltage and less, longevity, but you can kind of like do the calculations for power and they net about the same thing. Let's talk about your lead acid car battery. That's 12 volts. And that can be anywhere from 400 amp hours to 1,000 amp hours. So that's where you have, these are huge batteries. And then finally, something more relevant, like the Galaxy S9 lithium ion battery. That puts out nominally 3.85 volts, and that gives you about 3 amp hours. Okay, so that's kind of just rough ratings that we use for calculations. All of those are dependent on the technology too, because like the AA's and AAA's I gave you, these are all alkalines, 9 volts in alkaline. This is obviously lead acid, and then this is lead lithium ion. So if you went and got a AAA or AA battery that's made out of like nickel metal hydroxide or whatever that one. Hydride, it would be a different rating, be less than this. Okay, so then one last question on this stuff is, well, can you just pull an infinite amount of current out of these things? And the answer is no, you can't. So if you really want to get into like batteries and figure out what you're going to get out of these things, you have to actually go to the manufacturer's data sheet, and they have this really characteristic plot of kind of current draw versus the voltage. And let's do a 9 volt battery just so you can kind of see just rough magnitudes. They always kind of look like this. So you'll have like 1 milliamp, and then you'll have like, let's say this is 50 milliamp, this is like 100 milliamp, and it goes out to big stuff. And they always kind of look like this. These numbers are not going to be representative, but you start off at like open, okay, and it's higher than 9 volt. And then as you pull current, it starts going like this. Okay, and so it's going to drop, and as soon as you pull a current out of it, it's going to be, it's going to drop to some voltage, and it relatively stays straight as you increase the amount of current. And then once it gets out to some, it just drops. And what happens is that this knee right here kind of represents, where it's a slope of -1, it represents like the maximum current that you can pull out of it. So if you pull more than that, like if you hook this thing up and you tried to pull 20 amps out of it, it wouldn't even move, right? It would just be like, and it wouldn't even give you anything. And so you have to kind of look at the specific like curves from the manufacturer. So I'd actually go out to Energizer and get their curve for their particular battery and figure out exactly if it would work or not. Okay, the last thing though is that this is called a DC battery. And what that means is that versus time in general, this stuff just puts out a flat voltage. And so we say that batteries are DC. Now you can take a DC voltage and you can create an AC signal. Remember, an AC signal is just one that varies with time, so it'd be like a sine wave, but you have to put it through a special circuit, and that circuit is called an inverter. Okay, and that'll create the 110 volt AC signal that you'd see out of an outlet. You see inverters a lot of time, like when you're camping, you'll have like a battery and you plug in an inverter and turn it on, it'll give you the AC voltage. They also have a lot of these in like newer cars. So you'll actually take the 12 volt battery of your car, turn on an inverter, and you can actually plug something into like an actual outlet. So, okay, that is everything you've ever wanted to know about batteries, maybe even a little bit more. Okay, so that's our first source of electrical energy, and that's it. See ya.